The Physiology and Psychology of Pain, Chapter 2 in the Therapeutic Modalities text by Chad Starkey. This material corresponds to Chapter 7 in the Therapeutic Modalities, the Art and Science text by Kenneth Knight and David Draper. What is pain? Pain is an incredibly difficult concept to describe. Most of us can use different words to label the sensations felt during pain, and we pretty much all know what it feels like when we feel it. But pain can be extremely hard to define or even objectively measure. The IASP, or the International Association for the Study of Pain, brings together scientists, clinicians, healthcare providers, and policymakers to stimulate and support the study of pain and translate that knowledge into improved pain relief worldwide. The annual cost of pain in the United States is roughly $1 billion. Including 515 million lost workdays, according to the American Pain Foundation. Approximately 25 million Americans suffer from acute pain due to injuries or surgery. So what is pain? Researchers have been trying for decades to untangle the mystery of pain. An important breakthrough came in the mid-1960s when scientists discovered that the brain could change or modulate the nervous system in response to pain. Until then, it was believed that the nerve-brain pain connection was fixed and inflexible. Pain is defined as an unpleasant sensory or emotional experience associated with actual or potential tissue damage, or described in terms of such damage. Pain is subjective, which means that it is different and experienced differently among different patients. The physical display of pain also varies greatly from person to person. Some factors that influence the expression and perception of pain include past experiences, expectations, sociocultural background, personality, age, and gender. Men typically have a higher tolerance and threshold for pain. Women, many experts now agree, recover more quickly from pain, seek help more quickly for their pain, and are less likely to allow pain to control their lives. They are also more likely to marshal a variety of resources, from coping skills to support and distraction, with which to deal with their pain. The societal and cultural impacts of pain are extremely relative and can be seen demonstrated around the world. Take, for example, foot binding. This was the custom of applying painfully tight bindings to the feet of young girls to prevent further growth. The practice possibly originated among upper-class court dancers during the 5 Dynasties and 10 Kingdoms period in Imperial China, around the 10th or 11th century. It then became popular during the Song Dynasty and eventually spread to all social classes. Foot binding became popular as a means of displaying status. Women from wealthy families who did not need their feet to work could afford to have them bound. This correspondingly was adopted as a symbol of beauty in Chinese culture. Its prevalence and practice, however, varied in different parts of the country. Feet altered by binding were called lotus feet. Foot binding has resulted in lifelong disabilities for most of its subjects, and a few elderly Chinese women still survive today with disabilities related to their bound feet. Neck rings are any form of stiff jewelry worn as an ornament around the neck of an individual, as opposed to a loose necklace. Many cultures and periods have displayed neck rings as a sign of beauty, with both males and females wearing them at various times. In a few African and Asian cultures, neck rings are usually worn to create the appearance that the neck has been stretched. In Padawan, women of the Kayan people began to wear neck coils from as young as age 2. The length of the coil is gradually increased to as much as 20 turns. The weight of the coils will eventually place sufficient pressure on the clavicles to cause them to deform and create an impression of a longer neck. The custom of wearing neck rings is related to the idea of physical beauty. An elongated neck. Neck rings push the collarbone and the ribs down. The neck stretching is mostly illusionary. The weight of the rings twists the collarbone and eventually the upper ribs at an angle 45 degrees lower than what is natural. This causes the illusion of an elongated neck. The vertebrae do not really elongate, though the space between them may increase as the intervertebral discs absorb liquid. We can even see pain associated with sporting activities. Kevin Ware was a collegiate basketball athlete at the University of Louisville. Ware received widespread media attention when he suffered a disturbingly graphic compound fracture of the tibia in his right leg. This occurred during an Elite Eight game against the Duke Blue Devils on March 31, 2013. This occurred after he landed from an attempt to block a three-point shot. Players and coaches on both teams were visibly shaken at the sight of the injury. While lying on the floor of the court, Ware repeatedly said, "I'm fine, just win the game." Pain is referred to as the fifth vital sign and serves as an integral line of self-defense for the body. Pain serves to warn us that tissues are in jeopardy of being injured or have already been damaged. There are three main purposes for the sensation of pain. Pain is a reflexive response to dangerous stimuli. It serves to protect the body from further damage, and it reveals that something is wrong within the body. These faces show how much something can hurt. This face, the one furthest to the left, shows no pain. The faces show more and more pain, moving from left to right up to this one, the furthest one to the right. It shows very much pain. Instructions given to the child or patient would be to either point to or say which of the faces that shows how much you hurt. Although we might not like pain, it's important to our survival. The loss of pain perception leaves the body or areas of the body unprotected against serious damage and can leave a person unaware that damage has taken place. Congenital analgesia is very rare. Probably around 100 individuals have this condition in the world. It is the inability to perceive pain, and these individuals are prone to injury. Congenital insensitivity to pain, also known as congenital analgesia, is one or more rare conditions that a person cannot feel or has never felt physical pain. For patients with this disorder, cognition and sensation are otherwise normal. For example, patients can still feel discriminative touch, although not always temperature, and there are no detectable physical abnormalities. Children with this condition often suffer oral cavity damage both in and around the oral cavity, such as biting off the tip of their tongue or fractures to bones. Unnoticed infections and corneal damage due to foreign objects in the eye are also seen. Because the child cannot feel pain, they may not respond to problems, thus being at a higher risk for more severe disease. Despite sounding beneficial, it is actually an extremely dangerous condition. There are generally two types of non-responses exhibited by the patient. Insensitivity to pain means that the painful stimulus is not even perceived. A patient cannot describe the intensity or the type of pain. Indifference to pain means that the patient can perceive the stimulus but lacks an appropriate response. They will not flinch or withdraw when exposed to pain. Please watch the associated YouTube video entitled Grey's Anatomy Clip, Girl with Superpowers, as provided on your Blackboard course, as this demonstrates congenital insensitivity to pain. The nervous system includes the peripheral nervous system and the central nervous system. Neurons are the base unit of the nervous system, and neurons initiate and transmit nerve impulses. Dendrites are short and small processes that branch off the cell body. Some neurons may have only one dendrite, while others have many. Dendrites conduct nerve impulses towards the cell body. The more dendrites a neuron has, the more nerve impulses that neuron can receive from other cells. An axon is larger and longer compared to dendrites. Most neurons have only one axon. Myelin sheaths surround some nerve axons, but are mostly found in the peripheral nervous system. Myelin sheaths support, protect, and insulate the axon. The nodes of Ranvier are an area between the two myelin sheaths of the axon that is exposed. As a nerve impulse travels, it jumps from node to node. This jumping creates a saltatory conduction. Nerves that have myelin sheaths can conduct pulses a lot faster. This is a visual representation of continuous axon nerves and saltatory conduction nerves. The continuous nerve on the right takes much longer to process. The advantage to the saltatory conduction is that the impulse does not have to travel the entire surface area. Rather, the impulse can jump from node to node, thus allowing the action potential to move at a much greater speed. The thalamus is the gray matter in the center of the brain. The thalamus relays sensations to the appropriate supraspinal center to be interpreted. This includes all sensations except for smell. The cerebral cortex determines the intensity and the location of pain and also initiates descending pain control. The cerebral cortex is responsible for altering the perception and reaction to pain. There are three dimensions of pain perception: discriminative, affective, and cognitive. All pain has two psychological aspects. One discriminative, that is, that we can objectively gauge its intensity, location, and quality or type of pain, and the other is affective or emotional. The affective is the response to the pain. For example, does a person get emotional and display the pain outwardly, or do they keep it inside? Emotions are controlled by the limbic system, but regardless of the response to pain, it is clear that pain causes suffering, both emotionally and physically. The third dimension of pain perception is a cognitive effect. The cognitive effect is the individual's interpretation of the sensation of pain based on their own past experiences and expectations. This could include culture, ethnicity, sex or gender identity, experiences growing up, as well as many other factors. Many of us have experienced a child starting to scream at the sight of a needle. They know that they are going to get a shot. Based on their past experiences, they know that that last shot caused them some pain, and they are expecting this shot to be very similar in nature. Therefore, the affective response and cognitive perception to pain is displayed by an emotional reaction. Some of our affective response could be conditioned by our personality. Traditionally, extroverts tend to display their response to pain verbally and can sometimes be very loud. In contrast, sometimes introverts internalize their perception of pain and may become very quiet or silent when they're hurting. The more you know about your patient's personality prior to their injury or pain, it might help you to determine if their response is something you would or should expect. The emotional state of the individual may also play a factor in their response to pain. Take the basketball player Ware, who fractured his tibia on national television. His response was to make sure that his team won the game. He wasn't focused on his injury, rather he was focused on the outcome of a sporting event. Many of us can agree when you stub your toe when you're having a really bad day, it hurts a whole lot more than if you're having a fantastic day. Therefore, the emotional state of mind plays an important role in the perception and the reaction to painful stimuli. The pain threshold and pain tolerance are two importantly different factors. The pain threshold is the level or intensity of noxious stimulus that's required to alert the individual to a potential threat to tissue. The pain threshold is an objective measure, which means it can be quantified and measured experientially by introducing painful stimuli such as cold water, pressure, or heat and gradually increasing the stimuli until the individual reports pain. You can test out your own pain tolerance by pinching or squeezing your fingernail. When you reach a certain amount of pressure, there is pain, and that is your pain threshold. The pain threshold is often based on the recruitment of 8 delta fibers, a type of nerve that carries painful information to the central nervous system. Pain tolerance, on the other hand, is a measure of how much pain a person can or will withstand. In experiments, this is measured subjectively by the quantity or exposure to painful stimuli before the participant will withdraw from the stimuli. Pain threshold and pain tolerance are variable. Any individual can see variations in these measures at any given time. Pain threshold and pain tolerance can be influenced by therapeutic modalities. For example, cold modalities can increase the pain threshold by 89% and the pain tolerance by 76%. As was discussed in the previous lecture, there are different types of pain, either acute or chronic. As a result, acute pain has a sudden onset. It is the result of macrotraumatic injuries. During acute injuries, the kinins, especially bradykinin, prostaglandins, and substance P are released by damaged cells. Substance P is a potent vasodilator. Substance P is a key first responder to most noxious or extreme stimuli, for example, those with the potential to compromise biological integrity. Substance P is thus regarded as an immediate defense, stress, repair, and survival system. The molecule, which is rapidly inactivated, or at times further activated by peptidase, is rapidly released, repetitively and chronically as warranted in the presence of a stressor. These mediators cause activation of nociceptors. A nociceptor is a sensory nerve cell that responds to damaging or potentially damaging stimuli by sending signals to the spinal cord and brain. This process, called nociception, usually causes the physical sensation of pain in human beings. This painful stimulus ends when the tissue is healed. Chronic pain is the result of multiple microtraumatic events. The pain associated with chronic injuries lasts longer than that of acute injuries. The pain is often not related to the direct area of trauma or the primary injury, which makes these injuries difficult to evaluate and treat. The pain ends up becoming part of the person's daily activities and therefore is integrated into the person's life, which affects behavior and mood. This frequently results in depressed behavior symptoms and decreased feelings of happiness and life satisfaction. Chronic pain usually falls into one of two categories: nociceptive chronic pain or neuropathic chronic pain. Nociceptive chronic pain is caused by damage to body tissues and is usually described as a sharp, aching, or throbbing pain. Neuropathic chronic pain occurs when there is an actual nerve damage. Nerves connect the spinal cord to the rest of the body and allow the brain to communicate with the skin, muscles, and internal organs. Nutritional imbalance, alcoholism, toxins, infections, or autoimmunity can all damage this pathway and cause pain. Pain is normally well localized, but when pain is originating from an internal organ, it often is perceived as if it's coming from other areas that are far from the site of actual damage. This is called referred pain. Pain originating from visceral organs is poorly localized and may seem to originate from the surface of the body at some distance from the site of injury. Pain caused by an appendicitis is normally felt as originating from the abdomen. This is known as McBurney's point, which is a spot that's located on the right side of the abdomen, halfway between the umbilicus or belly button and the anterior superior iliac spine. Kerr's sign is pain in the left shoulder, which indicates trauma to the spleen. Pain referral maps, such as the one on the slide, can be helpful in determining locations of injury. Also remembering that sometimes pain in an area does not mean that that area is actually the area of damage. Referred pain happens because the surface of the skin and the internal organ were innervated by the same nerve during the development from embryo. During fetal development, visceral organs migrate from their original location in the embryo. Radiculitis is also known as radiating pain. It is a sign that a nerve or nerve root along the spinal column is under pressure from injury or inflammation. It is a common symptom of many spinal conditions and manifests itself as pain that travels the entire length of a nerve. For example, down an entire arm or leg. Radiating pain can also follow a dermatome map, such as the color-coded body picture on the left. Phantom pain is pain that feels like it's coming from a body part that is no longer there. Phantom limb pain can be mild to some of the most extreme forms of pain. Doctors once believed this post-amputation phenomenon was a psychological problem, but experts now realize that these are real sensations originating in the spinal cord and the brain. Phantom limb sensations may include feelings of coldness, warmth, or itchiness or tingling, but it should not be confused with phantom pain. Similarly, pain from the remaining stump of an amputated limb is not phantom pain. By definition, phantom pain feels as if the pain comes from the body part that no longer remains. The exact cause of phantom pain is unclear. It appears to originate in the spinal cord and brain. During imaging scans, such as a magnetic resonance imaging or MRI, or a PET scan, portions of the brain that had been neurologically connected to the nerves of the amputated limb show activity when the person feels the phantom pain. Many experts believe phantom pain may be at least partially explained as a response to mixed signals from the brain. After an amputation, areas of the spinal cord and brain lose input from that missing limb and adjust to this detachment in unpredictable ways. The result can trigger the body's most basic message that something is not right, which results in the feeling of pain. Because there are so many factors that can affect pain, it is important to be able to try to quantify pain. A perceived pain level is a person's expression of what one person feels. Pain assessment should include both the subjective and objective evaluation to properly document the level and the amount of pain that the patient is experiencing. The measure of pain is classified into two types of tools: multidimensional and unidimensional. Multidimensional scales often incorporate various components of pain, including affective and behavioral, whereas unidimensional scales reflect on only one dimension of pain, usually its intensity. The McGill Pain Questionnaire is a multidimensional scale. This is considered to be the gold standard of pain measures. It is demonstrated on the next slide. The numerical rating scale has the patient select a number representing his or her pain level Numbers are usually ranging from 0 to 10. Usually 0 is no pain, and 10 is the most excruciating pain possible. The difficult issue with the numerical pain rating scale is it can be difficult for some patients to conceptualize pain as a number. The visual analog scale is similar to the numerical rating scale. The visual analog scale is a horizontal or vertical line, usually 10 centimeters long, with verbal descriptors at the extremes indicating no pain and worst imaginable pain. The participant is instructed to place a mark on the line indicating the amount of pain experienced. Other variations of the visual analog scale include the numerical rating scale and the faces of pain scale, which was on a slide earlier in this lecture. The McGill Pain Questionnaire should be used during the patient's first visit to identify painful areas and to quantify the intensity of the pain. There are both advantages and disadvantages to using the McGill scale. The obvious advantage is that it is a multidimensional scale, capable of measuring many aspects of pain. The scale depicts changes in its 4 sections. This allows the clinician to evaluate a more comprehensive change over the course of treatment. In this first section, the patients are asked to identify localized areas of pain and indicate if the source of discomfort is superficial, which means it's external, or it's deep or internal. Mark an E if the source of pain is external, or an I if it is internal. If the source of pain is both internal and external, please mark a B. In the second section, the pain rating index, there are many different words that can be used to describe pain. From the list, the patient is instructed to place a circle around the word that describes the pain you are currently experiencing. The patient can only use one word for each category. For example, in the first category, the words flickering, quivering, pulsing, throbbing, and beating are used. The first word in the group is worth 1 point. The second word is worth 2, and so on. If the person chooses beating, it would be worth 5 points. The clinician will then add up the total number of words chosen to create an intensity score. A patient could have a high McGill Pain Questionnaire score of 20 by selecting a word in every single group, but could have a low intensity score by selecting just the first word in every group. In the third section, a ranking of the person's pain changes are dimension measured. Characteristics of the pain's duration, such as whether the pain is continuous, rhythmic, brief, or transient, are measured. In the fourth and final section, the intensity of the pain is measured as mild, discomforting, distressing, horrible, or excruciating. The intensity is also measured at its worst, least, and current level. The person is asked to rate the intensity compared to the worst toothache, headache, or stomach ache pain ever experienced. Some researchers have questioned the scale's practicality because it takes approximately 20 minutes to complete and another 5 to 10 minutes to score. The next section that will be discussed are pain theories. Afferent nerves are responsible for transmitting pain. These include the A delta, or group 3, and the C fibers, which are group 4. These fibers are mostly unmyelinated fibers, termed C fibers. There is also a smaller group of fibers with diameter from 1 to 4 microns, termed A delta fibers, and another group with diameters of 8 to 22 microns, termed A alpha and A beta fibers. The A fiber groups consist of myelinated fibers. The A delta fibers are small diameter, lightly myelinated nerves that transmit mechanical pressure, temperature extremes, or ischemic pain. These fibers are known as the fast pain associated with injury and are often described as rapid or sharp pain. These nerves have the ability to localize pain to a specific spot, also known as epicryptic pain. C fibers are smaller in diameter. They are typically unmyelinated afferent fibers that also respond to mechanical pressure, extreme temperature, and chemicals, especially from the inflammatory markers. The pain originating from C fibers are referred to as slow pain that is characterized by a dull, non-localized, and diffuse pain sensation, also known as protopathic pain. C fibers are the most abundant, primarily afferent in the human body and are the body's monitors for potential problems. C fibers are called polymodal because they respond to many different types of noxious stimuli. The speed of the sensation of pain is related to the diameter of the fiber. On the left, we can see a picture of a two-lane street. This is a representation of the C fibers, as they are the smallest fibers. These are considered slow fibers because the impulse can only move so quickly along a single pathway. On the right, we see a much larger nerve. We can see that it has multiple pathways, and so therefore the larger actually are faster nerves and the smaller are slower. The threshold of a fiber to externally applied electrical shocks is inversely related to the diameter of that fiber. Accordingly, A alpha fibers would have the lowest electrical threshold, or require the least current to evoke a discharge. A delta fibers slightly higher, and C fibers the highest. A beta fibers are from the mechanoreceptors such as hair follicles, Messinier corpuscles, Pacinian corpuscles, Merkel cell endings, and Ruffini endings. Free nerve endings arise from both myelinated and unmyelinated fibers in the articular nerves, whereas spray-like endings and corpuscles arise from myelinated fibers only. Nociceptors are specialized nerve endings or sensory receptors. They respond to potentially damaging stimuli, for example, mechanical, thermal, or chemical energy impingement. Nociceptors activate A delta and C nerve fibers, which relay the signal to the central nervous system, and then the signal gets interpreted as pain. Nociception is the ability to feel pain. It is the process of capturing potentially damaging signals, relaying the information to the central nervous system, and interpreting it as pain. Nociception and pain are closely related but are not the same thing. Nociception is the objective event. Pain is the subjective, emotional experience. Pain results from modulation of nociception by a host of factors such as heredity, psychosocial experience, prior pain experience, and general life stresses. Nociceptors are sometimes classified by their location around the body: cutaneous in the skin, somatic in the joints and bones, and visceral in the body organs. Or sometimes nociceptors are classified by their function. Mechanical nociceptors are lightly myelinated A delta fibers. They are larger and faster and therefore are considered to be the higher threshold mechanoreceptors, but result in sharp, fast pain initially. The nerve fibers are considered phasic, which means they dump out quickly but the pain returns. Polymodal nociceptors are unmyelinated C fibers. These fibers are smaller and slower in their impulse. This creates a slow, dull, achy pain and can be defined as tonic or long-lasting. René Descartes was one of the first Western philosophers to describe a detailed somatosensory pathway in humans. Descartes' manuscript, The Treatise of Man, was originally written in French and was illustrated, edited, and published posthumously, first in Latin in 1662 and then in French in 1664. Descartes described pain as a perception that exists in the brain and makes the distinction between the neural phenomenon of sensory transduction, today known as nociception, and the perceptual experience of pain. Descartes started describing pain as a spiritual and mystical experience. He theorized that pain was a disturbance that passed along a single nerve channel to the brain. This occurs when a specific nociceptor in the periphery is stimulated. This stimulation sends an impulse to the brain along 4 monomodal specific nervous pathways, resulting in pain. Monomodal means that the pathway can only respond to one type of stimuli, for example, heat, cold, touch, or pain. Specific receptors are a physiological fact, but the direct connection between stimulation of receptors and pain is a weakness in this theory. This theory does not explain the phantom limb pain, why people react differently to pain, or why some people and even animals have been trained to react favorably to noxious stimuli, such as the famous experiment with Pavlov and his dogs. We can see in this picture the stimulation of heat then would be taken up a monomodal pathway to the brain and be sensed only as heat. We could then see the same thing with touch. Unfortunately, this theory does not allow us to have pain and touch occurring simultaneously, or a polymodal experience. The pattern theory was developed as a reaction against the specific theory, and it denies the existence of pain receptors. It suggests that the pain occurs only when the rate and pattern of the sensory input exceeds a threshold. According to this theory, the intensity of the nociceptive stimulation evokes a pattern of impulses in nonspecific receptors that is interpreted by the brain as pain. The bottom line for this theory is slow-conducting nerve fibers carry pain. Fast-acting nerve fibers carry other sensations. Normally, the fast-conducting fibers override the pain. Under pathological conditions, the intensity of the stimulation in the slow system becomes much greater and dominates the fast system, resulting in pain. There are two problems with this theory. It is too general, and it does not account for the physiological evidence of the high degree of receptor fiber specialization. For example, when the eyes, a sensory receptor, are stimulated, they send impulses to the brain via the optic nerve. The contemporary definition of pain used by the IASP is based on the divisional multidimensional definition proposed by Malzek and Casey in 1968. These dimensions include the sensory discriminative, intensity, location, quality, and duration, the affective motivational, unpleasantness, and the subsequent flight response, and the cognitive evaluative, or appraisal, cultural values, context, and cognitive state dimensions of pain. These three dimensions are not independent, but rather interact with one another. Most of the contemporary theories of pain involve several types of polymodal receptors. Pain can travel along several different pathways, and it travels at three different levels or orders. The first order of pain transmission involves the afferent nerves, which are the ascending nerves. Those stimuli travel to the dorsal root ganglion. The second order includes the stimulus traveling to the dorsal horn and further up the ascending pathway. The third order is when the stimulus reaches the brain, which includes the thalamus and cerebral cortex. This drawing is of the pain transmission pathway. During the first order, the painful stimulus is recognized by a receptor. That painful stimuli travels up to the dorsal root ganglion, or the DRG, which is a sensory neuron. During the second order, the pain signal travels to the dorsal horn of the spinal cord and then is transmitted up the ascending tract. During the third order, the pain signal reaches the brainstem and the thalamus, which then transmits the signal to the cerebral cortex. Sometimes the pain signal is sent back down from the brainstem through the descending tract to the dorsal horn again. The gate control theory was proposed by Malzek and Wall in 1965. The gate control theory integrates the specificity and pattern theories. The gate control theory operates at the spinal level and proposes a gating mechanism as a pain control theory. This gating is located along the dorsal horn of the spinal cord and only allows one sensation at a time to pass through the brain. Pain and other sensory stimuli travel along both large and small diameter nerve fibers, and they converge at the T cell, which is the gate. The T cell, also known as a transmission cell, functions to transmit the pain signal to the higher center. The T cell determines which impulse will continue up or down the spinal cord and subsequently to other parts of the body. There is an inhibitory mechanism located in the substantia gelatinosa, or SG, in the dorsal horn of the spinal cord. The SG is the gate, or more likely the guy who has the key to lock the gates. Dull aching pain travels along small fibers, A delta or C fibers. Small fiber stimulation inhibits the SG, thus decreasing its effect on the T cell. The SG sends an inhibitory neuron to the T cell and is always active, constantly providing background inhibition to the T cell. Due to the SG's inhibition of the T cell, this is an explanation of why people may react differently to the same noxious stimuli. Sharp stinging pain travels along the large fibers or the A beta fibers. Large fiber stimulation facilitates the SG, thus increasing its effects on the T cell. This sends a strong sensory stimulation that can control pain by closing the gate. When activated by A beta fibers, it will inhibit T cells from transmitting the pain signal to the higher center. When it's inhibited by A delta and C fibers, it will not inhibit the T cell, but therefore pain signal will be conducted to the brain. As the gate, the T cell opens to allow the other sensory stimulation to pass through the action system. The action system includes all responses to pain, such as when you touch something hot, the reaction would be to remove the hand from the hot stove, jump up and down, or maybe even use verbal language to express that it was hot. This means that only one sensation is allowed to pass through the brain at a time. The gate control theory also proposes the concept of central control, which influences the gating mechanism and therefore the action system. The idea is that the pain center in the brain collects and integrates information from many sources such as vision, smell, memory, hearing, as well as from the large fiber and small fiber nociceptors and other sensory information provided by the body. Based on all the integrated information provided to the brain, the central control can either increase or decrease the response to pain. The gate control theory led to the development and use of transcutaneous electrical nerve stimulators, or TENS units. Unfortunately, the success of TENS application started poking holes in the gate control theory. There are several issues with the gate control theory. It does not explain the influence of drugs on modulating pain. Some application areas for the use of TENS are not anatomically related to the spinal column, so the gating mechanism would be ineffective. Placing TENS electrodes at the dermatome level associated with pain would be required to elicit the gating mechanism. However, further research has indicated that placing the electrodes a level above or a level below will often elicit a pain-relieving response as well. The concept of this theory is still strong. Some of the details have been proven to be inaccurate, but the concept is solid, and therefore the gate control theory still remains as one of the major pain control theories. The central biasing theory is a modification of the gate control theory. It involves all the original gating mechanisms plus the additional central inhibitory mechanisms. It modulates the T cell neurons as originally proposed in the central control and acts via neurohumorals, endorphins, and enkephalons. This theory suggests that at least two mechanisms of pain control via descending pathways. Portions of the cerebral cortex are responsible for emotion. They help facilitate the para-aqueductal gray or the PAG region and start a descending pain control mechanism. The PAG region activates the Ralphie nuclei, or the RN, which is a cluster of nuclei found in the pons that regulate serotonin. The Ralphie nuclei have connections descending the spinal level and have connections to the endogenous opioid system. This mechanism synapses with the spinal enkephalon interneurons. The release of the enkephalon interneurons close the gate, in which decreases the afferent traffic and results in a decrease in pain. The fiber travels from the C fiber to the spinal cord. It then goes to the midbrain in the PAG. Then it travels to the pons, down the descending pathway, where enkephalons are released, which block the afferent signal. Castell introduced a theory of pain after endogenous opioids were discovered in the human body in the 1970s. The body produces these three types of peptides that have an opioid-like property: enkephalins, endorphins, and dynorphins. To review this pain theory, the initial tissue response to injury and descending neural impulses must be examined. When tissue is subjected to injury, bradykinin, prostaglandins, and substance P are released into the tissue. These mediators influence the initial inflammatory response to injury. Bradykinin directly produces painful stimuli. Prostaglandin and substance P are a type of neurotransmitter and lower the nerve's threshold to bradykinin, which magnifies the perception of pain. Repeated or prolonged stimuli perpetuate the continued feeling of pain. In the spinal cord, opioid peptides are released to modulate pain transmission. The enzyme cyclooxygenase catalyzes the formation of prostaglandins. The blocking of prostaglandin synthesis by nonsteroidal anti-inflammatory drugs, or NSAIDs, is the base for using these drugs to control pain and inflammation. Over time, these chemical irritants released into the tissue diffuse and make a larger area hypersensitive to pain perception, explaining why pain becomes less localized over time in an acute stage of inflammation, making pinpointing pain later in the healing process difficult. Methylamine enkephalons also influence the release of pain modulators. Enkephalons are the natural endogenous opioids found in the central nervous system that are released rapidly for short-term pain relief. They counteract the effect of substance P in the SG and thus inhibit the transmission of painful stimuli to the T cell. Endorphins originate from the hypothalamus, which is where the pain threshold is influenced. The thalamus directs the sympathetic nervous system to gear up for a fight or flight, which involves the release of norepinephrine and adrenaline. Beta endorphins are released in the cerebrospinal fluid in the presence of severe stress and physical exertion, a process that is believed to be associated with so-called runner's high. Just as morphine is an addictive drug, endorphins can also create a strong desire in the runner to continue to run with the pain until the high is achieved. Endorphins can also be released through high voltage or low frequency electrical stimulation protocols that inhibit noxious stimuli. Beta endorphins can provide up to 4 hours of natural pain relief. This slide serves as a review of the pain control theories. The gate control theory occurs from a non-noxious stimuli such as touch or pressure. It inhibits pain through an ascending pathway. It affects the second order, and its most important key factor is the substantia gelatinosa. The central biasing theory occurs from a non-noxious stimuli. It inhibits pain through the descending pathway. It affects the second and third order, and its most important key factors are the periaqueductal gray matter, pons where norepinephrine is released, and the Ralphie nucleus, which is releasing serotonin and enkephalins. The endogenous opioid theory occurs from a noxious and motor stimuli. It inhibits pain through a descending pathway. It affects the second and third order, and its most important key factors are the anterior pituitary, which releases beta endorphins, and the Ralphie nucleus, which releases serotonin and enkephalins. Remember that pain is always contextual to the individual. It can help if you give your patient some context. Rather than the phrase on the slide, "Next time, if you expect me to believe you are a 10 out of 10 for pain, you better be on fire or have a stick protruding from your eye." I frequently describe a 10 out of 10 pain as the worst pain possible and that you would need to be transferred to an emergency department immediately. This will be your in-class assignment for the next meeting. Please draw, explain, or demonstrate how the different pain control theories work. You must explain the theory in detail of how it works, what's actually going on, but also give an analogy comparing how the theory works to a real-life situation. You can write out your thoughts, draw pictures or diagrams or whatever to explain your perception of the theory. You will also need to find a way to explain these complex theories so that a child or your grandparent or someone who has no knowledge of these subjects could understand. You will need to describe the following theories: gate control theory, central biasing theory, and endogenous opioid theory. Please bring to class paper, colored pencils, markers, or any other resources you think would be helpful to create pain theories in your own words. You can have drawings, you can explain it in words, or whatever means necessary to help yourself understand these principles. You will be sharing your work with your classmates upon completion. Quiz number 3 will be open until Tuesday, September 13th at 9 a.m. Please remember that the quizzes must be completed prior to attending class. The quiz will be over Chapter 2 in the Starkey text. It will be 10 minutes and worth 10 points. Please don't get confused and review the pain threshold versus pain tolerance, nociceptive and neuropathic chronic pain, pain theories, including the specific theory, pattern theory, and contemporary theory, and pain control theories such as the gate control, central biasing, and endogenous opioid theory. Exam 1 will be on Thursday, September 15th. For class, you will log into the computer. A review for the exam is available online. You will need to be using Internet Explorer or Google Chrome only. I will remind you on the day of your exam that these two browsers are the only ones that work with our setup. You will have 30 multiple choice questions as well as short answer and fill in the blank. Some of the concepts that could be on the test include these topics. There will be 6 additional bonus points. I will remind you of this as we get closer to the exam, but I just want you to be prepared so that you're ready for our first exam.